Questions about anything? Things are going all right? Okay. What's that? They're going ideal. All right, so today, I don't know why I started recording because I'm going to really bring on the screen in a second. Today I got some toys.
Yay!
Yay! Let's see if I can put all the same way to start with. Doesn't really matter as long as we all kind of start in the same place, but what I want you to do is, with your square, I want you to line it up to where it starts with the 1 on the upper right-hand corner, so you may have to flip it over if it's not there already. 1 on the upper right-hand corner and the 2 next door on the upper left. Okay. All right. So just so that we're all starting in the same place so that we can follow along with what we're doing. All right. So I'll show you the bigger one, except I don't have numbers on mine. Okay. So the idea here is that imagine that your square is there. You want to figure out the number of different ways that you can pick your square up and put it back in the same position. You might turn it, flip it over, what have you. How many different ways you can do that in one move? Okay, so picking it, for example, picking it up and putting it down is, it didn't do anything. That's okay. So the reason why the numbers are on there is to help keep track of something that's different, right? So what you might want to do. So like maybe a second move, you could pick it up, turn it, and then drop it again. Right? That's one thing you might do. What the numbers are there for is to try to keep track of where things go. So one way you might write that is maybe you'll start with the 1, 2, 3, 4 up top, and just keep track right below it as where the ones go. So the one that we pick it up and put it back down again, everything stays in the same spot, right? So I would write that like that. So the idea behind this is the top is your initial starting position, and the bottom is where the things get moved around to. Okay. So the first thing I want you to do is see how many different ways you can do that. Okay, so do that first. You can chat about it too. You don't have to just do it on your own. Make sure that we do it all the same. I'm going to let you work on it with your toys and work with this. So let's just label them in the order that I have them on the board, going top to bottom and then moving over to the second column, just so that we're all in the same place. Okay. So the operation, and again I said think of these as functions. So the operation is going to be function composition. I'm going to do f of g of x, essentially, right? When you do f of g of x and you plug a number in for x, which function do you do first? You do the g, take that output, and then put it down, right? So what I mean by this is if you want to do, say, R90 and operate it with h, remember the thing that's listed down the column is always listed first. The one across the top is the one that's listed second. If you want to do R90 operated with, and I'll use a star for right now, because our operation here is function composition. When I write it that way, even though I'm writing R90 and then H, you would do the horizontal flip first and then the 90-degree rotation. Okay? Does that make sense? If I write R9, if I want to fill in this block right here, that would be R90 operated with H, right? The thing that's on the left gets written first. The thing that's up at the top gets written second. But it's function composition, so you work inside out. Okay. So when you're filling out this table, that's what you want to do. Do your horizontal flip, do your rotation, and then see which single element does that same thing. So if you do a horizontal flip followed by a 90-degree rotation, what do you get? If you do a vertical reflection followed by a 270-degree rotation, what do you get? Okay? So see if you can fill out your table. I'll just stand here and sweat while we're doing that.
You pointed more at
No, that's okay. It's just really warm in here. It's because all the bricks heated up for 3 days. So now we're just in a brick oven. So the brick oven cools off. I brought another fan. I was trying to bring some of that cooler air into the office down the hall to make a pipeline, if you will. I don't know if you ever go back and look at them or not.
Yeah.
Yeah? Oh, okay, cool. So it actually helps?
Yes.
Oh, wonderful. Cool. Let's just go right by row. Everybody okay with the upper left-hand corner? That was pretty straightforward, right? You just keep rotating the same direction. You get back to where you started eventually, and then just keep going again. Okay. All right. What about this first row at the end here? Yeah. Oh, everybody got? Okay. And the next one? Okay. Pardon me. And then the next one? Okay. Before we keep going, and we'll keep track of this later on as well, notice that up there in the upper right block, if you will, it's all the reflections, right? And nothing got repeated, either across in a row or down a column. All right, let's go the next row. I know there's more to fill in the next row. What do we have? Okay. Oops.
Sorry.
That's all right. I just wrote what you said. This must be R270. Yep.
I thought I'd say 10.
That's okay. It's just my brain. It's fine. Is that what everybody got? Okay. What's the next one? Yep. Next one? R180. Yep. And then the next one should be H, D, V, R90, R270, and R180. Yeah. All right. So. All right. So let's look at some properties of this table. One of the properties that I mentioned, we're actually going to talk about later when we get to quotient groups. I talked a little bit about this with quotient rings earlier. Notice that you've got this block up here in the upper left-hand corner. At the same block, kind of. It's not exactly the same, but it's the same elements in that block in the lower right-hand corner. And then likewise in the other two corners with the reflections. If we treat them like they're cosets, we've talked about cosets with rings, right? If we can imagine cosets, notice you can do operations on cosets and form a new group, if you will. Because notice if I take anything in here and operate it with anything in here, it lands in there. If I take anything in here and operate it here, it lands in here. Likewise over there. Or if I take anything in here with itself, it lands over there. So we're going to get that coset notion of in groups as well as we do in rings. Okay, so it's going to follow along that way. Do you see an identity with respect to this operation? What is the identity going to be? Yeah, the R0, right? You pick it up and put it back down again. That's the identity operation. Okay. So this, whatever this structure is that we've created, we have an identity relative to the operation. Another thing that we notice is that there is something that can get me back to the identity. Everything's going to have an inverse with respect to that operation, right? Notice that R0, R180, and all the reflections are all their own inverses. The inverse of R90 is R270, and vice versa for R270. So everything has an inverse with respect to the operation. The other thing that we don't necessarily see from the table, but the operation is also associative. So if you wanted to do 3 of them, operate 3 elements, do 2 at a time, you could either do the first 2 and then the third, or do the second and the third and then operate the first up front. So the operation is associative. That's a little hard to check, because if you were checking associativity, I'd have to use any element for the first thing in my product, anything in my second, and anything in my third. So I'd have to check how many products. 8 times 8 times 8. Make sure it worked. That's a lot. Associativity typically is a more difficult thing to check directly. Good news is that most of the operations that we're going to do will be associative because we already know they're associative. So like this is function composition. Even though we're using letters to represent the functions, we're doing function composition, which we know is associative. So that's not a problem. Okay. All right. One more thing to notice is that the operation is not commutative. Okay? The operation here is not commutative. Notice that if I do the vertical flip followed by 90-degree rotation, I get that main diagonal flip. But if I reverse it, I get that off diagonal flip. Right? So this structure is not commutative under this operation. All right. This particular structure is what we call a dihedral group. And this is any dihedral group is the group of symmetries of a regular n-sided polygon. You know what regular polygon means? All the sides are equal, all the angles are equal. Okay. And so what I mean by symmetries of this is that exactly what you did, right? We know this, that we can pick the square up, rotate it 90 degrees, put it back down. It looks like that, except for the way we numbered the vertices, it looks the same, right? That's what we mean by a symmetry. So for any regular polygon, you'll have n ways that you can rotate it and it look the same. Because I can take any vertex and move it to any of the other vertices, including itself. And then there's also going to be n reflections every single time. Okay? So this is an example of a dihedral group of a square. The notation for this is dn. The n is representing the number of sides of the polygon, or the number of vertices of the polygon that we're using. The size of this, remember we use the vertical bars for cardinality of the set. The size of this set will be 2n, which is why I said I was looking for triangles rather than squares, because it would have taken a little bit less time. But the triangles that I had were isosceles right triangles. I didn't have regular triangles, and I didn't want to cut out a bunch of triangles. I didn't want to make Lainey cut out a bunch of triangles. All right. I will draw the triangle up here on the board real quick to show you the difference between the reflective symmetries when you've got an odd number of sides versus an even number of sides. Not much of an equilateral triangle, but pretend like it's equilateral. Obviously your rotations are 120. Hopefully it's obvious. I got to take this 120 degrees to get there, 240 to get there, and then 360 will get back to 0. So there's going to be 3 rotations. Notice that all of your reflection lines, in this case, go through a vertex and are perpendicular to the opposite side. Right? That's different than what our reflection lines were for the square. I had one that cut the square in half vertically, right, with a horizontal line, one that cut the square in half horizontally, the vertical line there. Right. So when you've got even versus odd, you get different reflective lines. but you still have this idea of half of your elements in your set will be rotations and half will be reflections. And that's why we got 2 times the number of sides. That makes sense? Also, one of the things to notice from this particular operation table, again, when you do a rotation with a rotation, it's another rotation. If I do a rotation with a reflection, it's a reflection again, right? And that makes sense if you think about what you do with the square or anything else. If I rotated it, the same side's up. If I reflect it, now it's upside down. Right? So if I do a rotation and a reflection, in either order, it has to be a reflection. Right? And then again, if you do 2 reflections, if you flip it upside down, and then flip it upside down again, you're face up. So it has to be one of the rotations. Because the rotations are all the face up things. That makes sense? Okay. Another thing to notice, and we mentioned that with the function notation, which I said we're going to come back to later. That'll be on Tuesday. When we come back to that function notation, notice again that these dihedral groups are all a subset of the possible permutations if you if you number the vertices 1 to n, because the vertices have to land on other vertices, right? So the 1 has to get mapped to a vertex, the 2 has to get mapped to a different vertex, right? But we don't get all possible permutations, like I mentioned with the square. I can't say take the square up, twist half of it, and then place it back down again. That's not a rigid motion. So you won't get all possible permutations, but you do get a subset of the permutations. And that's something else that we'll come back to later as well. All right. So let's see. Mentioned again, the operation's associative. There's an identity, and everything has inverses. Okay. So this is exactly what we use for the definition of a group. So your dihedral groups are groups. So as a definition here, let's let let's let G for group be a non-empty set with a binary operation star. I'll start by using a star to denote the notation. Later on, we'll stop writing the star and understand that when we juxtapose 2 elements together, we mean do the group operation. So if I wrote FG and its function composition, then I know it's function composition, not multiplication. The only exception to that is if we have an additive group, we will still use a plus sign. Okay. All right. But for right now, we'll use the star. Then one of the notations for a group is to label the set of elements that you're doing and then say specifically what the binary operation is. We call this a group if, well, the first thing we make for a group is making sure that our binary operation is associative. So A star B star C is the same thing as A star B star C for all A, B, C, and G. The operation has to be associative. We also need an identity element. With groups, we typically use E to denote the identity element. Now this is the group. We only have 1 operation in a group, not 2 like we did with rings. Okay? Every group has to have an identity. So there has to exist an identity element. So this would say that A star E is A, which is also E star A for all A and G. We don't say multiplicative identity anymore. This is just identity for a group because there's only 1 operation. It may be an additive identity if it's an additive group. It may be a multiplicative identity if it's a multiplicative group. But notice with our dihedral group, it was a function, right? It was the identity function in that case. Okay. Right. The last thing is for all A and G, there exists some other element in G such that A star with B is E, which is the same thing as B star A. So everything has an inverse with respect to the operation. These are the three requirements to be a group. Notice it doesn't say jack squat about being commutative. Right? So groups can be non-commutative. If the group is commutative, so if A star B equals B star A for all A, B, and G, then we say that G is abelian. If we know what the even though I use that kind of ordered pair looking notation for the group when I defined it, if we know what the operation is for the group, we don't bother writing it every single time. We just say G is a group if we understand what the operation is. Or if it's a property that all groups have to have regardless of operation. So abelian is the name that we give for groups that are commutative under their operation. Okay. You'll see some books write it as a capital A versus a small a because it's named after Niels Abel, Norwegian mathematician, I believe. But it's been used for so long that most books just write it lowercase. Okay. All right. What's that? What did you say?
Dumb joke.
What was the dumb joke? I love dumb jokes.
Notice it.
The appealing chameleon. I like it. It's fun. All right. So let's look at some examples of some groups. Some are pretty straightforward. If I look at the integers under addition, I get an abelian group. In fact, every single ring that we've dealt with is a group, is an abelian group under addition. There's nothing special about Z here. Okay? Every single group, every single ring, just looking at the addition part, is an abelian group. The ring axioms satisfy all the axioms for groups under addition, plus addition's commutative. That was what we required for rings, right? So there's nothing special about Z. Now, is Z under multiplication a group? Is multiplication associative? I should say integer multiplication, yes. Does integer multiplication have an identity?
No. Yes.
Yes. Yeah, that's where I was going next. Does every element have an multiplicative inverse in the integers? No. Okay. So no, not every element, and not every non-zero, not every element, period, in Z has a multiplicative inverse. That's fine. I get it. They're related though, right? Okay. All right. There is a special name for Z under multiplication. As a matter of fact, if I go back up to your definition, if you only satisfy number one, we call that a semigroup. So, in particular, every single ring under multiplication only is a semigroup. Okay. If you have 1 and 2, we have what's called a monoid. So if it's associative and has an identity, we call it a monoid. So that last example that I wrote down, the integers under addition, the integers under multiplication is a monoid, and not a group. There's a lot of study of monoids, in particular for factorization. And again, one of the reasons why we care about factorization, besides the fact that trying to break things down into pieces to analyze them makes sense because it's a lot easier to look at smaller pieces than it is bigger pieces. Factorization pops up, as I mentioned, with doing codes, for example. So being able to do factorization types of things is a big area of study in algebra, or at least in my neck of algebra. All right. So just a couple of other ones. If F is a field, any field, then the non-zero elements of the field under multiplication is an abelian group. Because we know in a field, every single non-zero element has a multiplicative inverse. So it satisfies the group axioms. And for fields, we require commutativity as well. So the non-zero elements of a field form a group under multiplication. The set of units of a ring form a group under multiplication. Again, by definition, a unit of a ring has a multiplicative inverse. So then that particular set will satisfy all the group axioms. So in the last minute here, let me give you a couple of more interesting examples. That looks like a lot of notation, doesn't it? That's ugly. Okay. This is what's referred to as the special linear group of n by n matrices over a field F. That sounds really hard, doesn't it? It's a lot of words. It's not that hard. This is the set of all matrices, n by n matrices, where your elements come from a field. So maybe they're all rational numbers, maybe they're all real numbers, maybe they're all complex numbers, such that the determinant is 1. So you just take every single matrix that has determinant 1. You want to make sure you have field elements that you're using so you can do fractions in your elements, doing multiplicative inverses. So the set of all 2 by 2 matrices over the reals that have determinant 1 forms a group. That's the special linear group. If you change the S to a G, you get the general linear group. And instead of making it specifically equal to 1, you just say the determinant's not 0. Now, why would I want the determinant not 0? What do you know about matrices from linear algebra? A matrix is invertible if and only if its determinant is not 0. So we're making sure we have multiplicative inverses in these groups. That's why we do these. Okay. So each of those are groups under multiplication. Okay? That's the important part. We're trying to make sure we have multiplicative inverses. And from what you know from matrix multiplication, they're non-abelian groups. They don't commute. Okay. So this gives you a couple more examples of groups that are not abelian. Most of the ones we deal with end up being abelian, so you maybe have hard times with examples. Two prototypical examples you have now that are not abelian. Dihedral groups are not abelian. Matrix groups are not abelian. Matrix groups under multiplication are not abelian, I should say. Under addition, they are. All right. We'll do more of this on Tuesday. I'm not going to give you new homework. Hopefully today was okay with the toys. Good?